Hello, everyone, and welcome to the Meetup that focus on coroutines in Kotlin. Now, this Meetup is for software developers with some experience in Kotlin, and especially with knowledge and experience in concurrent programming. If you have no idea what concurrent programming is, I doubt if you will succeed to catch up and understand the basics of coroutines. If you do have some background, some understanding in concurrent programming, then this meetup is for you. If you know nothing about Kotlin, still this meetup will be a great start for you, especially looking at one of the highlights the Kotlin programming language has to offer us. So, coroutines in Kotlin. Well, the first question would be, what is coroutine? What is a coroutine? So, what you can find on the Kotlin website is what you see over here, is a definition that we can agree with, we can adopt. It is a great definition. Coroutine is an instance of suspendable computation. Instance of a suspendable computation. So stick to the two words, suspendable computation. It is conceptually similar to a thread in the sense that it takes a block of code to run that works concurrently with the rest of the code. Now, let's put this definition aside and let's try to check another definition I found in another place saying the following. Coroutine is actually a word composed of two words. We have the word routine, which is a function, and we have the word co, the beginning of cooperative. So coroutines is when you have two functions or more that execute in cooperation with each other, so that when one method pause, the other continues, and then when the other method, the other function pause, then the first continues, something like that or similar to that. But before we move forward, let's try to clarify a few things about threads, process, or maybe we should start with process and then explain what a thread is, and then explain what a coroutine is. Then it will be simpler to use, on your end, to use coroutines as a replacement for threads. But let's start from the beginning. Process. Well, as you probably know, we can execute on our machine one process, two process, three, four, well, actually lots of processes. Each process is usually a single application. So usually you have on your computer up and running multiple applications, multiple processes. Each process is executed separately from the others. Each process has its own memory area. And the CPU, let's assume that we have only one CPU, the CPU split the time between those processes. Now, it happens so fast that we get the illusion that those processes are executed concurrently. Well, if our computer has more than one core, then probably a true concurrent programming happens if the computer has more than one core. But if the computer has only one core, then it is certainly an illusion. So this is what happens when we have multiple processes on our computer. The split of the time, the split of the core, the CPU resources between the processes is done by the operation system. Okay, what is a thread? What happens when we create threads? So when we create threads, then we create those threads within the scope of a specific process. And what we get is kind of small programs that are executed concurrently or not concurrently, but we get the illusion that they are executed concurrently And that happens thanks to the operation system. Every thread we create, whether we code in Java or Python or Kotlin or C#, every thread is mapped to a native thread the operation system maintains. So there is the operation system. The operation system maintains native threads, and each native thread is responsible for a specific thread in our code. It works. And well, till the emergence of Node.js, most server-side handled huge traffic by having multiple threads working concurrently with each other. As of the emergence of Node.js, we could see a shift to another direction where we have only single thread, one single thread, but there is a queue of jobs, and thanks to that queue of jobs, the computation resources are exploited in a great way, and sometimes the performance is even better than having multiple threads. One of the problems when having multiple threads is the native thread that each thread is connected to. When having code running on top of the virtual machine, it can be a Java virtual machine, it can be a Python virtual machine, it can be a .NET virtual machine, no matter what. When creating a thread, a new thread, that takes huge resources because there is a need to create a native thread. The operation system needs to create a native thread, and then there is a need to connect between the native thread and the new thread we created, and that consumes huge resources. We will get back to that later. Okay, so we explain what does it mean having multiple processes on our machine. We explain what a thread is, and now the question, what exactly is a coroutine? Well, another definition for coroutine would be lightweight thread. Why is that? Well, when we create a program that includes multiple coroutines, then when the program is executed, then we can see how the execution is jumped from one coroutine to another, from one function to another function to another function, and then back. So it is kind of multiple threads running concurrently, just that there is one big difference between working with coroutines and working with threads. And the difference is that we don't have native thread in the background. It is a huge change when moving from threads to coroutines, because it allows us to have multiple coroutines without having multiple native threads managed by the operation system, as it happened when working with threads. Okay, let's move forward and see a sample for coroutines in Kotlin. I will try to explain a bit the syntax, but don't worry if you don't understand it completely. So this is the ID. I have it already prepared for you. Now, there is a small change I did before I executed the code. If you go to the configuration, you can see that I added this option, -d kotlinx.coroutines.debug. And I did it so that when I execute the code, whenever I ask to print the name of the thread, thread is the same class you know from Java. Current thread returns the reference to the thread object that is responsible for the execution of the code. Name, well, every thread has its name. So when I print the name, in addition to the name of the thread, we also get the name of the coroutine that is executed. So what do we have over here? So we have the main method. If you're not familiar with Kotlin, this is the equivalent main to main in Java or C++. Now, when we execute the main method, look what happens. First, we call the method message in order to print the number 1. Now, if you look at message, you can see that whatever I pass over is printed together with square bracket. And then what I ask to print is the name of the thread. Just that in addition to the name of the thread, we also get printed the name of the coroutine. Then launch creates a new coroutine within the scope of the coroutine that was created over here. This is possible, and we will talk about it later. We can create a coroutine that includes multiple coroutines inside of its scope. So this new coroutine is responsible for printing 2, 3, world A, 4. Now, as you can see, the next print doesn't come from this coroutine, and it doesn't come from the next coroutine. It comes from line 25, coroutine 1. And then we have a print coming from line 26. And then you can see that the rest sometimes comes from coroutine 2 and sometimes comes from coroutine 3. So you can see coroutine, this is the coroutine 2 that's responsible for printing 2, 3, 4. 2, 3, 4, and kind of concurrently with this coroutine, we have this coroutine printing 5, 6, world B. Look, world B is printed before world A, and 7, somewhere here it is. So this is a simple demo for creating multiple coroutines. And in this case, we have those coroutines, the ones that we create using the launch function. In the scope, with those two coroutines, the one that we create in line 11 and the one we create in line 18, are created within the scope of the coroutine that is created over here in line 9. And as you can see, there is only one thread. Its name is main, the main thread. And within the scope of this thread, we have output coming from coroutine 1, coroutine 2, coroutine 3, and we could have more coroutines if we wanted. If you're not familiar with the Kotlin programming language, I will just say that when you invoke a method such as run blocking or launch, and the function expects getting a reference to an object that represents another function, you can pass over what we call a lambda expression. And this entire code is a lambda expression till here. And then we have this lambda expression we pass over to the function launch, and something similar happens again. If you are familiar with Kotlin, but you're not familiar with lambda expression, check out my course on Udemy, Lambda Expressions in Kotlin. I explain every aspect in this topic in detail, step by step, everything. Okay, so we saw a small demo for coroutine. Let's move forward. As I said before, some will consider coroutines as lightweight threads. And we can show a demo for using coroutines as lightweight threads. Take a look at this code sample. This code sample includes the method main, and the method main includes a call to run blocking. Run blocking creates a new coroutine and block the main thread, and only when that new coroutine is ended, only then the function main will be ended. So the word blocking means blocking the thread through which run blocking was invoked. Now, repeat is a function I can call and pass over a number. In this case, I pass over 200,000, asking to perform this lambda expression 200,000 times, meaning that this function launch will be invoked 200,000 times, and each invocation, a new coroutine will be created. Now, try to create a program in Java that creates 200,000 threads. I doubt if that program will execute successfully. 200 threads means 200 native threads the operation system needs to handle. It is a way beyond the capability of most computers. Give it a try. But here, this code runs successfully. We don't have 200 native threads. The split of the computing resources, the split of the CPU between those 200,000 coroutines is done not using native threads the operation system managed, but it is done using code, simply code that developers wrote. Well, Coroutines, it is a library, a simple library that developers in JetBrains develop for the Kotlin programming language. And when using that library actually replaces the native threads we were using when working with threads. And in addition, provides us with many more capabilities we're not familiar with when working with threads. So back to this code sample. Let's execute this program. And as you can see, it works fine. Well, in this case, each thread just prints something to the screen. There is a small delay, but it works fine. And as you can see, we have 200,001 coroutines running in this sample. And as I have just explained, the split of the computing resources we have from the CPU is done by the library using code that developers wrote, not using native threads, as it happens when working with threads. Okay. One more topic. Well, you can imagine that before this meetup, I was thinking, what would be the best topics to pick and cover and explain without getting into too much details? Because when you get into too many details, it's not a simple topic to cover. So the third topic is what we call structured concurrency. In reality, there are many cases where we need to perform multiple tasks concurrently and in asynchronous way, each one of them, due to limitations such as accessing database, sending a request to a web service. Those activities have small delays. So the best way to complete those activities, those operations, would be using asynchronous function. Or in other words, let's connect to those servers we need to connect, to those databases we need to connect using coroutines. So we can have multiple coroutines and we can place them within the scope of another coroutine. And the promise we get is that the big coroutine that includes in its scope multiple other coroutines will end only when all the small coroutines it includes end. So just imagine a server side that handles a request coming from a user, and the meaning of handling that request is sending requests to multiple databases. In reality, it happens a lot. And we want to have code that it would be simple to maintain. So we can have separated multiple coroutines, each one of them connect to another database. And have those coroutines together in the scope of one big coroutine. The one big coroutine will come to its end only when all the other coroutines it includes ended. So when the big coroutine ends, we can move forward to the next step of handling that user, having all data we need from all web servers. And the code will be simpler to maintain because we will use coroutines. So take a look at this code sample. It's a very simple demo. We call run blocking. Run blocking stops the thread, in this case the main thread, but it could be another thread. And only when all coroutines that are created in this scope of this big coroutine ends, only then the coroutine that run blocking created ends. And in this case, only what happens is that the main function ends. But actually, we could also take the previous code sample, this one, the first code sample we were using. Just imagine big coroutine that includes multiple other coroutine. This is one coroutine, this is another coroutine, maybe we have more coroutines. The big coroutine that includes all other coroutines will end only when all other coroutines it includes ended, only then. So we can use this structured concurrency we can easily create on the server side in those cases when we need to connect multiple servers, multiple databases, multiple RESTful web services for every request that arrives from the users. Okay, so this is basically what I planned for the meeting. If you are already into Kotlin, I just want to remind that in order to use coroutines, in order to execute these code samples, you need to update your Gradle file. You need to add a dependency, as you can see over this line, for using the Kotlin coroutines library. Not everything that Kotlin supports already there. For example, serialization, coroutines, and there are more samples. Libraries you need to install. So you need to update the dependencies with the libraries you need. Only then it will be possible to use serialization, coroutines, and so on. Okay, so now we move to the Q&A. And thank you for attending the meetup and for watching the video. And I wish you all the best.
Thank you.